wrong.
No, but there's going to be 2 sections from his book, which I have.
Okay.
I need a file.
No, you don't need the bucket. Okay, so this is Math 496, 696, the numbering based on whether you're a grad student or not. Computational Algebraic Topology. Now, that name in it of itself requires some explanation, which I will do. There's some logistics. This is kind of a complicated exercise, in part because what I'm going to attempt to do is take you from mathematics of roughly 1800s and push you all the way up to the early 2000s. So we're going to go all the way from, well, what was modern mathematics, I suppose, mathematics evolving over 3,000 years, so 1850 or so is modern, to pretty close to the cutting edge. This is the kind of work that has been done by a lot of people. In fact, I'm currently on the wrong time zone. I just came from Seattle from a conference where we were talking in a session on computational applied topology. So I gave a talk there, and there were lots of other luminaries of the field as well, not me, talking about this kind of material. So this is very, very recent work that we're going to end up talking about. So let's see here. What is this about? This is about computational algebraic topology. So let's sort of tear apart the name. And then we'll tear apart the syllabus so we have some idea of what's going on in the course. Computational algebraic topology. Let's start at this end. Topology is, of course, the study of math where we can't tell the difference between a coffee cup and a donut. As many of you might be familiar with, this is the study of space under continuous deformation. Some of the earliest ideas in topology kind of were formed around some of the early thoughts of Riemann, so 1850s. When he was thinking about manifolds, the early definition of manifolds, generalizing some of the ideas of Gauss, but was really picked up and made into its own subject by Poincaré. And the early 1900s, late 1800s, or roughly 1900s. There's a reasonably famous paper from 1904 where he poses the now reasonably celebrated Poincaré conjecture about understanding whether or not a given manifold, i.e. an object defined by Riemann, was in fact a sphere. Various properties leading to your inference that yes, I'm looking at a sphere. That problem was only very recently solved by an amazingly detailed and complicated work by Grigory Perelman, which led to him being awarded the Fields Medal, although he did not accept it for various political reasons.
Nor the money.
Nor the money, yeah. Apparently he's still living with his mother. Anyway, straight character.
Maybe the mother would have taken the money.
No comment. Okay, so that's what topology is. And in particular, topology yields spaces, and you'd like to study these spaces, understand whether or not these spaces are the same or not. If you think about just the spaces on their own, well, it's kind of hard to tell them apart, kind of hard to discriminate them, and it takes a lot of work. So one of the things that Poincaré in particular had invented with some collaborators was a notion of discriminating spaces using algebra. Now, algebra also is kind of something that perhaps many people here have studied. Many people have taken linear algebra. Yeah, good, that's prerequisite to the course. But also there's things like abstract algebra, which again, roughly this time period, 1850s, plus or minus a bit. A lot of work by Galois, a lot of work by Sylvester, a lot of work by folks studying matrices and that sort of thing. The things we're going to be studying with is linear algebra, which, roughly speaking, was started around the mid-1800s again, although not quite so definite as a single person. So lots of ideas about linear algebra in the mid-1800s. Linear algebra kind of lay dormant until about the 1950s. And that's where the computational part came in. And the reason for this, of course, 1950s is what big major thing was invented then?
The computer.
Of course, the computer. And the notion that you could take these big arrays of numbers that were kind of annoying to work with and let something that didn't care that they were annoying work with them was a big boon. Now, since that time, since the 1950s, we've had an explosion of work in computational linear algebra. That's helped a lot. And it's helped to the point that we can start talking about computing very, very large matrices. Millions of rows and millions of columns can be contemplated. If you think about what Google does, Google is a company that specializes in actual fact in really, really big sparse matrices. We're talking about billions of rows and columns. That's why they need so many computers, because they don't all work on one big matrix individually. They all work together on a big matrix. So this has come a long ways. Now, that's the words on their own. Now, what's algebraic topology? That's a specific kind of study of topology. So let's sort of tear that apart and really understand what that means. And I'll remove the computational from the discussion for a moment. And let's just sort of zoom in on the different types of topology there are. So there's point set topology, which here at American University is what course? Math. We just finished it last semester.
440?
Yeah, 440 and 640. That's point set topology. And basically it is based off of sets of points, as the name suggests. The other big chunk, well, there's several other big chunks of topology. There's differential topology. Which isn't really covered in a class here. And there's algebraic topology, which is trying to study the same kind of objects as we do in point set topology, but using some algebra to make some of the discriminations a little easier. Now, algebraic topology, in fact, divides into two different major worldviews. One of those worldviews is called homotopy theory. This is really the coffee cups and donuts. It's also actually really hard. The algebraic invariants you get under homotopy theory, they are in fact somewhat better than you would get with point set topology. But in fact, they're still really hard to work with. Sufficiently hard that it's still an open question to figure out what all the homotopy groups of spheres of arbitrary dimension are. The spheres are pretty basic. So if you don't know what the homotopy groups of the sphere is, well, you're kind of out of luck. So homotopy theory is not what we do when we're trying to compute things, because as I just said, it's a currently unsolved problem to compute with them. So instead, what we're going to focus on this class is homotopy's little sibling, homology. And that's what this course is going to talk about. So we're going to talk about homology. And the real benefit of homology is that homology brings in linear algebra. Homotopy theory brings in abstract algebra. And if you've ever taken a class in abstract algebra, you can realize that non-abelian groups can be kind of hard to work with. Abelian groups, on the other hand, are pretty easy. And in fact, we're going to even cop out even more in this course. We're going to work with vector spaces, which are even easier yet. So we're going to focus on computing homology. Now, in order to do that, I'm going to have to tell you what homology is. And I'm going to need to bring you up to speed with computing it. And the name computational should suggest that computers are going to be involved. So now let's have a look at the syllabus to see how the course is laid out. So first of all, got listed up at the top, office hours and all that, good logistics. I've got links that you can link into the page. This is actually an HTML page. If you go to Blackboard, this is a live HTML. All of these underlined things are indeed links as they look, which is handy because if you look down under the course description, there's a whole bunch of textbooks. They are all optional. You do not need to buy a textbook to take this course successfully. On the other hand, you might want to. First one on the list, and I think it's probably the best one around, is this book here. This is my copy. Elementary Applied Topology by Robert Greist. It's my postdoc mentor at Penn. This book, unlike most textbooks, is relatively inexpensive. It's about 30 bucks. So I suggest you pick up a copy. It covers far and wide beyond what we're going to talk about in this course, though. This has got many, many things, and it has got some really fabulous pictures. In fact, in the topology community, Robert Greist is famous for his pictures, because his pictures are amazing. And in fact, he told me at one point he really wanted to be a graphic artist, but he realized graphic artist probably meant starving graphic artist, and he decided math was a more lucrative field. Now, whether or not that's actually true is quite another matter, but he's doing pretty well. So anyway, this has got all sorts of interesting applications of the ideas of topology we're going to use. So, highly recommend. Next on the list, also inexpensive in the sense of you don't actually have to pay for it, is Alan Hatcher's Algebraic Topology. I would have brought it, but I left it out to one of you, and I haven't seen it since. That's okay.
It's fine.
It's fine. It's safe. Okay, good. In any event, it's available online. You can buy it, again, inexpensive, but you can get the whole book as a big PDF if you like as well. It's a great read. It's not very computational, though. It's just, as the title suggests, algebraic topology and nothing more, nothing less. But it is the reference. So if you ever have a question about some definition or anything like that, it's in there. There's a computational homology book by Thomas Kaczynski and various others, Konstantin Mushaikov and Marian Roshek. I actually know all three of them. Actually, I think I know all of the authors that I've listed here. That book focuses very much on a specific kind and way of computing homology that happens to be very easy, where spaces are built up with cubes. Think Minecraft. This is the book of how to do computational topology in Minecraft, although they don't think it's that way. I actually did think about actually using Minecraft to teach this class. That would be cool, but then I realized that there was a lot of additional logistics I didn't want to deal with. Anyway, there is my book on the list. I feel kind of embarrassed promoting my book because it is way too expensive, but such as it is. Many of the examples and exercises we'll work through are exercises in this book, but again, you don't have to buy it. Do not feel obligated. And I also list a book, Computational Topology by Edelsbrunner and Heirer. That's a great book that describes the mainline approach to computational topology with all of its details. It's actually a fairly advanced read, but quite good. So if you want a good reference, that's a good reference. And finally, there is a massive reading list of papers that you can look at. That will come to the fore in a little bit. So, let's see, logistics. There are homeworks. There are 6 homeworks due roughly every 2 weeks. They're by hand. You've got the first one there. The idea is I want you to be able to talk about the theory in class, to be able to do the simple computations by hand so that you thoroughly understand what's going on. And then finally, the next thing is I want you to actually get some programming projects and actually write some software. Yeah?
You say by hand, you mean you can't write it up in LIX or LaTeX?
No. You can write it up in LaTeX, but I want you to do the computations out by hand. You can, of course, use a calculator to help you with the numerics. That's fine, because mangling matrices all day is not very much fun. I get that. That's why I don't use any bigger than 4x4 matrices. But I mean, actually do out the computations by hand. You'll see how that goes, especially when we get into the lecture today. And then finally, the programming projects. These are all up on Blackboard. Actually, projects 1 and 2 are right now on Blackboard. Project 3 will be soon, but it's not done yet. And these involve programming in Python. So, get Python on your computer. The first project has detailed instructions about the Python requirements that you need in order to make the thing work, what libraries you need. And the way that I set this up is that it is a test-driven methodology. So I have a bunch of tests that your software needs to pass in order to complete the project. Now, what I've additionally done is I've given you, compiled into Python bytecode, my solution. Point of the matter is, you can't read that, it's not human readable. On the other hand, you can at least try it out. And you can see, oh, this is how this piece of code works if I give it various inputs. This decouples the various problems from one another, so you can work on them in any order. So that if, say, problem 3 depends on problem 2, and you haven't gotten problem 2 working, you can use my solution for problem 2 to test your problem 3. So it gives you a lot of help to make sure you work through the process. Credit goes to Professor Dietz for figuring out how to do this. Okay, so questions on that sort of thing thus far? Okay. There will surely be questions when it comes to actually programming. Yeah.
I presume we are allowed to work together on this project.
Yeah. Yeah. All right. Other questions? Yeah.
Does it list somewhere what libraries you need? Or?
Yep. In the instructions for problem 1, which are up on Blackboard.
Oh, okay.
So you can go download the instructions for problem 1. They'll tell you what libraries you need, how to install them, and in fact, if you download the bundle of Python code for problem 1 or project 1, and you've got the right libraries, the tests should all pass out of the box. So in particular, you go run all the tests, everything should say test pass, test pass, test pass. And if one of the libraries is missing, you get a whole bunch of errors. So I've verified that on my machine, which has all the dependencies, everything works perfectly. So if it doesn't come to office hours sooner rather than later, it'll get you straightened out. And that is true for all of the programming projects. The thing that I have always noticed when running programming projects is the sooner you come to office hours with problems, the quicker we can get you straightened out and things move smoothly. The intention of this course with respect to programming is to build a complete computational topology library, computational homology library, so that you should be able to take data from experiments, such as in fact are described in these various books, and run them through your code and get useful answers out. Now, I will say this. We're not writing heavily optimized code. We're writing simplified code. The optimizations have been found to be very important. Much of the progress over the past 5 years has been in optimizations. That actually brings us to the final exam. I don't expect you to write these optimizations, but what I want you to do for the final exam is, rather than a pencil and paper exam, I want you to give a presentation. We're going to go find a paper, and I can help you find a paper. Read the paper from basically the last 5 or 10 years. Look at an algorithm, look at some theorems or whatnot from applied topology or some applications, and give a relatively short 15-minute presentation on the contents of that paper. If you like, we can videotape it, we can post it on YouTube, we can service to the community. If you don't, that's fine too. And so I've got some suggestions of things that might be good search terms to get you started, although I'm happy to give you a lot more detail. There's a lot of interesting algorithmics papers. In fact, there are some that now, having come back from this conference, I didn't have time to put in here. There are other cool things that have been done literally within the past year. So there's a lot of neat stuff that we can talk about. It's all very timely. Okay. Now, as far as videos, I've noticed this class is being recorded, and I, in fact, have gotten very used to lecturing in front of a camera so that we can go back and look at it. I've listed a whole bunch of lectures from a tutorial on sheaf theory that I gave this past summer. Sheaf theory is not computational algebraic topology. It's something fancier, but it's built on top of algebraic topology. And so many of the background material that I talk about in those lectures are, in fact, kind of relevant. So I've listed the most useful ones here, so you can go have a look at them, watch the videos. They're not very long. All the slides are there, so if you want to look at the slides carefully, and there are additional programming exercises that are part of that. So if you want a little extra digging into the programming, it's available. Okay, and let's see, is there anything else that we want to talk about? Ah, yes, the schedule. It's worth noting the schedule is not very orthodox. These classes of computational topology, of which there are a few, I've been able to nail down about 5 different places where there are classes taught on this subject. There are probably more that haven't really advertised themselves to the world. What I'm doing that's a little bit unique about this is we're going to start with the algebra. We're going to build out the algebra first, because I think it's a little more straightforward and it's a lot more computational. Once you've got the algebra in hand, then we bring in the topology, and then we head straight for the modern stuff, which is the theory of persistence. So we're going to build all of these sorts of things together, and we're going to buttress it with the homework and with the projects, so that you'll build something that can talk about homology right off the bat, bring in the topology so we can do simplicial homology, abstract simplicial complexes, which is kind of topological space, and then talk about persistence, which is how you make this robust to errors and noise so that you can work with real data. Before we go any further, questions on this? Okay, well then, let's start moving down the algebraic path. Now I mentioned right from the outset that we're starting with linear algebra, and we're going to build on top of linear algebra. So in order to do that, let me dust off some of the tools of linear algebra that we'll need. So linear algebra is done where? It's done in vector spaces. What is a vector space? Well, it's basically an abelian group with some additional structure. So let's put down a definition. So what's a vector space? A vector space is a set with some additional structure. Set V with two operations. Plus and a times. Just to keep things simple and to tie them down to the computer, we're going to deal with real vector spaces. So the scalar multiplication is by real numbers. Now, in actual fact, they'll be floating point numbers, but don't let that bother you. Just assume we're dealing with real numbers. Occasionally, we'll run across some issues in the code where there's a difference between real numbers and floating point numbers. We'll round off, we'll defend against that, and then assume it never happened. Okay, so it has two operations, such that what? Well, the first thing is that V with the plus is an abelian group. And the second thing is that this multiplication here times and plus distribute. And just to be very explicit, 1 times V is equal to V for all V. 0 times V is equal to 0 for all V and V. And A times B times V is equal to A times B times B. You've got this associativity if A and B are real and V is in B. Okay. So that almost gives you a group structure on sort of it's like a group action. So that this group of multiplication, or not quite group of multiplication, on R, it plays very well with the structure. Okay. And the distribution law, let me write that out explicitly just so you see that. Well, A, B, there's two ways to think of it. First of all, addition and multiplication distribute like this. And additionally, oops. So there's two kinds of distribution. And that's what I mean by distribution. Of course, this is quantified all over all AB in R and BW in big B. Okay, so that thing is a vector space. Notice right off that we've got some notion because of the abelian groupness of the plus. I have some notion of negative vectors, or inverse vectors. They're sort of the negatives. And by a little bit of manipulation, you can realize that, in fact, based on the distribution law, that negative vectors, in fact, ought to be negative scalar multiples. Oftentimes, I'll leave off the dot when I'm talking about scalar multiplication, as is customary. Okay, so just get that on the board. That's a vector space. Now, there's some key facts about vector spaces. The first key fact about vector spaces is that I don't need all the vectors, usually. I only need some smaller set, a basis. So a basis for a vector space allows me to write all the other vectors as a linear combination. And there's some notion of dependence and linear independence, so we need to get those kind of concepts out of the way. So a set of vectors is linearly dependent. Let's see here, I'll call that set A, subset V. V is my vector space. If there is some way of writing a linear combination that wipes the whole thing out. If the sum, say 0 to however many there are, let me just index over I. So I'll just say for all the AI's. In fact, let me be even more simple about this. Let me say A sub V times V, where V is in my set. Capital A is equal to 0. So there is a set A sub V. V is in A. And this is a collection of real numbers. Such that this weighted sum, i.e. linear combination, vanishes. Usually you think of A as being finite set, it doesn't have to be that. So if I take a collection of coefficients, a bunch of real numbers, apply one real number to each vector in my set A by scalar multiplication, and then I sum them all up using the vector sum, I get 0. Now, if this is an infinite set, you ought to do some kind of limiting process. This being a computational class, I'm going to brush that under the rug. So, assumption. A is thereby avoiding all sorts of convergence issues that might crop up. Because this is, after all, a computational class. My computer's not going to be happy if I ask it to do an infinite task. Or at least the computer will happily run it. I will be unhappy because I'll never get an answer. Okay. So that's what linear dependence means. And then a basis is a maximal linear independent set. So definition, in fact, if V is a vector space, a maximal linear independent set is called a basis. And the observation is theorem. If finite set now 1 through Bn is a basis for V, and this is capital V, and little v is in big B, then there are A0 up to AN, A1 up to AN in R. Then I can do the same kind of sum and recover V. So there's this reconstruction theorem. Okay, so I times the elements of my basis and N. I forgot to such that. Such that this occurs. So I can reconstruct any vector in my vector space using this basis. Second theorem is that all bases have the same cardinality. Okay, cool. So thus far, everything should be fine in the sense that this is stuff that allows you to start setting the stage. Once you've got bases, though, then you can start doing some really useful things and computational things. The important point is bases. Number one, bases all have the same cardinality. The second thing is that bases might contain different vectors. In which case, the AI in the theorem will differ. So you change the basis, you'll change these AIs. You won't get the same AIs. Now that's an important lesson, because when we start manipulating vector spaces, we can, in spirit, really manipulate these coefficients. But you should always realize these coefficients are referenced to a basis. Okay. So that gets us to the point of manipulating vector spaces. So if I have two vector spaces, I want to talk about how I might relate one to the other. And this is actually part of an important story. See, the important story is that mathematical objects in the road are not very interesting. Well, I mean, they're kind of interesting, but this is about as far as you get. You get a characterization theorem like this, you're done. If, rather than having reals in front, and I ask for integers or some other ring, I get a little more complicated characterization theorem than merely cardinality. But manifestly, there's not a lot more to say. Things really start to get interesting when I start translating between them. And this is the thread of thought that I want to follow. Following thought, that is, that of a linear map. V and W are vector spaces. Function f from V to W as sets is linear if for all A comma B in R, B comma W in V, a bunch of equations. So basically F distributes over all the various operations you can think of. F of A times V is equal to A times F of V. Notice this whole thing is in W. This is in W. This is just a real number. And similarly, F of V plus W is equal to F of V plus F of W. And of course, you could encapsulate this in one whole thing that says linear functions preserve linear combinations. It's a nice slogan. Okay, the moment you have a linear function and you have a basis on V and W, you can write this whole thing down in terms of these coefficients AI. And that's what a matrix is. What's that?
You say that last part again.
Ah, okay. So once I've got a basis for V and a basis for W, then all of the coefficients that I have, all of the weights for describing a vector in V or a vector in W, and what happens to the vector in V when it passes through F, can all be described in terms of these coefficients, these weights. And those are characteristic to F. That's the matrix associated to F. And here we go.
It's the matrix associated to F.
With those two bases.
Those two bases.
Absolutely.
Yes.
It's with respect to those two bases. Change the bases, the matrix changes too. So, if V1 up to Vn is a basis for V, W1 to Wm, that could be different, is a basis for W. And let's say here x is sum from 1 to n of the VI's. This is in V. Then, dot, 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 what's this f of x? Well, now I can start making use of all the axioms I have kicking around here. First of all, I can write out the coefficients, the coordinates of x, just by copying this formula in here. Then I can use the second of these distributive laws with a linear function f. So this is linearity number 2. And what that does is that says I can just write this thing out. So I. Now, using linearity 1, I can pull out the AIs. Now, each of these f of VI's, where are they? They're vectors in what space? W. So they're a vector in W. So I can rewrite them in terms of the bases associated to W. So I can write each of these VI's in terms of the W's. Now I got I already in play. Now I need another letter here. Might as well use J. And now with a little bit of mangling of sums, thankfully these are finite sums, so I can just do this more or less with impunity. Let me reorder things around a bit. Oops, I is not in play quite yet. There we go. I, J, W, J. Oops, where my AIs go? All right, AI, W, J. There we go. Okay. So what have I done? I've just reordered sums. I've reversed the order of summation and have rearranged things a little bit. What's in the parentheses is what you would normally write with row into column. Oops, 1, 2, etc. Matrix multiplication, row into column, matrix multiplication. So this is matrix multiplication. There it is. So, given a basis for the domain and the codomain of my space, the domain and the codomain of my space, if I have a linear map, then I can describe it by this big array of numbers via matrix multiplication. Okay. Now that was a whole lot of review. Now I want to start breaking out of the review. And really the whole power that we're going to leverage for computational topology is we're going to say, got one matrix. That's what you did in linear algebra. I'm going to say, what happens if I got more than one? What if I have a whole pile of matrices? A whole string of matrices, one after the next, after the next, after the next, after the next, after the next. I make a big long string of these guys. In fact, study of these objects has a name. It's called homological algebra, based around the study of homology, which is the object that we're going to be spending this whole semester computing and studying. So we want to really understand what happens when I have not just one matrix, but a whole string of them, that they all fit together. And this is where it's useful to start drawing things not so much with all these matrices quite yet, but as diagrams. And the diagramming things helps you organize in your brain what's going on. So much from one matrix. Now let's start doing more matrices, and let's start understanding what happens. And this is going to lead us into some pretty interesting territory algebraically, pretty quickly. Okay, so what if I had more than one matrix? Now, this is where it's useful to come pre-prepared with some good examples. All right, so let's consider, let me diagram out. This is a two-dimensional vector space. R2, two real numbers. I have lots of choices of bases here, and I'm basically saying that I've really got bases with size 2, and I can pick them as I desire. Here's another two-dimensional vector space. Here's yet another two-dimensional vector space, and finally a one-dimensional vector space. I'm going to represent the linear maps between them as arrows. A diagram that looks like this has a special fancy name. This is called a quiver representation.
Yeah, it's the arrows.
Yep, I've got a whole pile of arrows floating around. This is a quiver representation. In fact, a quiver is just the diagram without the R's floating around. It's just the pile of these arrows floating around. That's a quiver. And a quiver representation is I start dropping in vector spaces and writing in matrices. So let me write in a matrix here. And let me write in a matrix here. And a matrix here. Okay, so I got a bunch of matrices. Now, what I'd really like to understand, and what homological algebra is all about, is trying to make sense of what happens to all the vectors in each of these spaces and how they fit together. Now, if we look at it here, I don't really necessarily know, which vector is where and whatnot, because, well, like all sorts of stuff can happen. Well, I should really ask myself, what happens to a basis here? Well, something happens to a basis here. What happens to a basis here? Well, something happens to it, etc. And they somehow fit together. The bases here and the bases here interact through these coordinates, for instance. And the bases here and the bases here interact, again, through these coordinates. Now, one of the things that is an awful truth about bases is that they're not canonical. Any given vector space can have a whole bunch of bases. The basis in which I've written this matrix might not be really ideal for telling you what's happening. I may have chosen a poor basis here, and I'd like a better one to tell you what's going on. Now, we'll talk a lot more about how to do this choice of basis as we move along. And in particular, this kind of quiver representation plays an important role in the theory of persistence. This particular one could crop up there. In fact, I can cook up an example where that would be the case. But let me first show you how a better choice of basis tells you something kind of interesting about how this thing fits together. And here's the right choice of basis. And I'm going to write it down in a special kind of diagram. And we'll talk about what that diagram means. So this is a vector in R2. Surely, it has two components. First component is 1, second is negative 1. Here's another vector. These are not the basis in which this matrix was written, but let's ask ourselves, do these vectors paired together form a basis? Are they linearly independent?
Yeah.
And is that linear independent set 2 in size? Yes. There's 2 of them. Great. So there can't be any more because this is 2-dimensional. Okay. So what happens to this first guy? What happens to this matrix, or this vector rather, when I multiply it by this matrix? Row into column, row into column. What do I get?
Ones?
Let's see.
2 and 2?
Okay, let's do it. Let's
Negative 2.
all right, guys. This is already good. Row into column, that is 1 plus negative 1. 0. And again, 0. Okay, what about this one? What happens to this one?
I'm just going to get the second column back.
I'm just going to get the second column back, which of course is not 0. Now, 0 kind of holds a special place in a vector space, doesn't it? The 0 vector is the additive identity. Somehow not very interesting. And furthermore, what happens to the additive identity under any linear map? Nothing, right? Multiply the 0 vector by any matrix, that stays 0. Change the matrix, still 0. Not very exciting. Now I'm representing these basis elements by dots. I'm going to extend them out, following their lifespan as they move through this diagram. This one here is going along. What happened to it? It got turned into 0. So it doesn't quite make it over to here. It sort of ends before it gets there. This one, on the other hand, keeps going and ends up being a new vector. This vector. So this guy ended with an untimely death. This one continued. Okay? Now, is this alone a basis for this vector space? No, it's kind of missing something. I need another vector that's linearly independent to this one to make a basis. Now, you could pick a whole bunch of different possibilities. Let me tell you a particularly opportune choice, and I'm not going to reveal how I picked this quite yet. In fact, I'm not going to reveal how I picked this for quite some time, until later on in the course. This happens to be a particularly opportune choice. Now, are these two vectors linearly independent? Yeah. Why?
You can't multiply 1 by any scalar than the other.
Absolutely, right. So these two guys now form a basis. Again, probably not the basis that I was thinking of when I wrote this matrix down, but certainly they form a basis. Now, let's again trace the history of these two vectors. What happens when I multiply this vector by this matrix? Well, row into column, what do I get? 0, 1. That's not 0, so this guy made it all the way to here. What about over here? What happened to this guy? Multiply by this matrix by this vector. Yeah, -1, -1, exactly. So also did not end up 0, so it made it to the next stage. Now, what happens when I multiply this matrix, or this vector by this matrix? I get 0. So this one doesn't make it all the way to the end. On the other hand, this one makes it all the way to the end. I've drawn some kind of funky picture here based on the history of these bases. Now, I've chosen the bases very carefully to make it very clear to you what's going on. What's happened is this is a 2-dimensional space. When I map it through this matrix, only 1 dimension survives. This matrix projects 2 dimensions and squashes it down to 1. Now, there's left over some new part of this vector space. That leftover part that was never touched by the output of this matrix, never touched by the range of this matrix. That part, however, is still part of this vector space. I shouldn't ignore it. Now, if I then take this matrix here is full rank. You can see that actually just by looking at it, it's already in reduced echelon form. So this has full rank, so what does it do? Well, it takes bases to bases. So this basis maps to a new basis, different coordinates, but still a basis. This matrix does not have full rank, and it projects out this guy here. This thing here is called a barcode diagram. And it's a really handy way for understanding the structure of a quiver. Now, what's perhaps not obvious, in fact, more than perhaps not obvious, this is mathematician speak for being really facetious, actually. It's totally not obvious at all, and in some cases it's wrong. This barcode diagram determines, in fact, this barcode diagram determines everything. It tells you everything to know about this quiver representation. And interestingly enough, there are some quivers for where this works and some that doesn't. And there's a very deep theorem proven by Gabriel. So, theorem by Gabriel for linear quivers, or quivers that are one after the other, after the other, after the other, like this. Their representations are characterized by barcodes. Rather, they're classified. Which is to say, if you hand me a quiver representation where it's just a sequence one after the other, after the other, after the other, of linear maps, of matrices, one into the next, such that I can matrix multiply all the adjacent matrices as I go, then I can describe what's happening on the level of vector space isomorphisms by way of this barcode diagram. Terrifyingly, if you give me some other weird quiver, you might not be able to do that. There may be additional structure beyond this barcode diagram. In fact, Gabriel's theorem, which was proven quite recently, 1971. It's a fairly recent theorem. Actually says a bit more. It says whenever the quiver is in the form of something called a Dinkin diagram, these things have interesting, strange, and somewhat mysterious shapes, then the representation is classified by barcodes. So more recent work, recent as in, I think, 2013, extends that list a little bit more. That was done by actually one of the guys who was an office mate when I was a postdoc in Penn. And that was subsequent to both of us leaving Penn. So this is still an extremely active area of research. There's a lot of neat things that can be figured out from barcodes and trying to understand how much barcodes constrain the resulting quiver. Now, there's a lot to be learned here. And there's a lot of structure that I want to delve into and look at specific quiver representations. Because 1971, when I said at the beginning of this discussion that Poincaré was the person that thought of homology, thought of topology and such. So he didn't wait around until 1971. Poincaré died well before then. So he was actually studying a very specific class of quiver representations, those called chain complexes. And chain complexes are those that have some nice additional structure to them. And in particular, chain complexes are those quivers, linear quivers like this, one after the next after that, sequences, whose barcodes have a very particular form. But this never happens. All the bars in the barcode basically look like this. And I'll explain that in a much more prosaic way. But putting this barcode framework out there is very handy because this is going to crop up at the end of the course and play a really important role. And it'll play an important role throughout as well. Although if you do a search for barcodes and homology, all the papers will be fairly recent. Yeah?
So if I'm given one of these things and I know that the barcode is important, I want to build the barcode up.
Yeah.
The way that I do it is I start with any basis, and then if I end up with that kind of thing where one of those bases maps to null, then I have to complete the basis for the new vector space.
Yes.
That's kind of the algorithm.
Yes, and how you complete the basis is important. You can't just pick any old way to complete the basis to come up with a good barcode.
Okay.
I had to choose this one very specifically. And similarly here, etc. So choosing that initial basis element is actually the subject of what the algorithms for computing these barcodes do. Because they have to do a little bit of thinking ahead to figure out what the right choice is.
Are there also rules for the initial basis?
Absolutely. Absolutely. And that's going to be kind of obvious in just a few minutes. Actually, let me use this diagram here, up to the part that I've shown. What was this? This was okay. So let's just focus in on this part of the barcode. Just focus in on this part of it right here. What happened when I mapped through this matrix, this basis? Well, one of the basis elements went away completely. It was in the null space of this matrix. Another word for the null space that we tend to use in homological algebra is the kernel. I don't really know why there's two names. Mathematicians seem to prefer kernel, and engineers and computational scientists tend to prefer null space. Sometimes I've been told there's a technical difference, then I've been told that there's not. As far as I'm concerned, the same.
And both of them are all vectors that map to
All
zero
vectors map to 0. That's right. So this guy is in the kernel. 1, -1 is in the kernel of this matrix. 0, 1 is in the kernel of this matrix. And it'll be important to find kernels, and we'll see that in just a moment. Now, what can you say about the kernel of a matrix? Well, it's somehow a subspace of the original domain, right? In fact, the kernel of this matrix is the subspace that's all multiples of this thing. Take any scalar multiple, it still maps to 0. These two guys put together forming a basis. Well, all of the kernel is just all the guys that have a non-zero coefficient here and a 0 coefficient. And if I put any non-zero coefficient here, game off, it's not in the kernel. Okay. Now, this matrix has no kernel at all. This matrix does. Now, subspaces are kind of useful in that they tear apart the different parts of a matrix. And there's an important theorem about that. You can see it kind of standing right in front of you here. With this matrix here, what's the dimension of the kernel in this matrix? 1. What's the dimension of the image of this matrix? The dimension of the image of the matrix is 1, not 2. The dimension of the codomain is 2. The dimension of the codomain is 2. As in,
Difference between the image and the
okay. That's a very good question. So, and in fact, this is playing right into the next theorem I want to state and remind you of. So suppose F is a linear map. The domain of F is V. The codomain is the entire space. W. The image of F it's the set of all W in W such that there is a little v in V with F of little v is equal to W. All the possible outputs, that's the image. The kernel of F is the set of all v in V such that F of V is 0.
You said that the kernel of the second matrix, you said it was 0 or you said it was empty?
It is 0. It's not empty.
Yes.
It's not empty. The 0 matrix certainly does map to 0. If you have a linear map, the kernel is never 0. As in, or never empty. It is always 0. It's never empty. It's always, it always contains 0. Could contain more, as it does in this case. Yeah. You have a question, Brian?
No.
Okay. So the difference between the image and the codomain is merely what I put on the output. But the image is what I've actually exercised in the output. So if you look at this matrix, the image is all the multiples of 1, negative 1. The codomain is R2, all vectors in R2. But the image is just 1, negative 1. The kernel happens to be 1, negative 1, but that's more or less an artifact of the basis. If you just focus in on what's happening to the vectors here, what's happening is it's taking one dimension of the domain and mapping it to 0, and the remainder of it persists and goes into the image. Yeah?
Just hypothetically, if I chose an initial basis vector,
Mm-hmm.
who ended up being either a scalar multiple or the exact same vector as what I got for the second basis, how would I convey that?
Okay, so you're in a situation where I've put in a vector and I multiply through.
For example, if I chose 1, 1, 0, 1 instead of 1, negative 1, 0, 1.
If you chose 1, 1, and what?
And just 0, 1.
0, 1.
I think that.
Does that work? Let's see, if I put in 1, 1, then I...
Like maybe just 1, 0, 0, 1. Perhaps the easiest.
1, 0, 0, 1.
Right. I get the exact same vector.
I get the exact same vector out. Right, okay. Yeah, because it yields the same vector. Right. So what's happened here is it's telling you what is the dimension of the image?
What are the dimensions?
It's just 1. I've only got the and so in fact what that's an indication of, by what I'd like to write down as a theorem, is that's an indication that you know from that inference alone that the kernel has got to be of dimension. So the kernel, the dimension of the kernel and the dimension of the image are related. This goes on the name of the dimension theorem. So, theorem. And I'm going to make this now specific to Rn and Rm. Then, well, what's true? Well, the dimension of the kernel of f is related in some fashion to the dimension of the image. Yeah, the dimension of the kernel is m
minus
the image. So the dimension of the kernel is m minus the dimension of the image of f. There's even a dual statement that involves n as well. And that, how does that go? Anyone want to guess how that might go?
What was the?
So this is the statement. It says the dimension of the kernel of f is equal to m minus the dimension of the image, which you can see right from this diagram here. M is 2. The dimension of the kernel is 1, so 2 minus 1 is 1, which tells you that I've got one vector that keeps on going. One vector that was left unscathed by this matrix, not sent to 0. Yeah, there's another space here that I haven't written down.
Yeah.
There's another space that crops up. It's what was right here, in fact. That guy's got a name. That's called the co-kernel. The co-kernel is, well, it's something a little bit weird. It's a strange vector space. It's a vector space that kind of is parameterized by all the vectors in W that cannot be expressed but as an image of F. That's right. But it's not the total list of them. It's something a little different. So it is in fact something a little different. And how it works is it's the following. It is the vector space. Call it vector space K, where W is the image F. Well, in some sense. Plus k. Basically, I'm adding on the vectors of k. So the way we write that is like this. And this guy here, this is called a direct sum. And basically what it means is concatenate the bases. So I take a basis for the image of f, and I take a basis for k, I concatenate the bases, and I, lo and behold, get a basis for w. It's sort of a strange way to write the thing down. Sort of a strange way to write the thing down. And then, but with that in hand, then you can write down the right theorem here. Write down the analogous statement. M is equal to the dimension of the image of f plus the dimension of the co-kernel. Now this is a little bit weird, this co-kernel of f. And unfortunately, or fortunately, depending on your view at the moment, this understanding what this co-kernel does actually really is the key to understanding how quivers work. And in fact, where have you seen a construction like this before? Probably not in linear algebra, just based on pedagogy. What's that? In group theory, yeah. That would be the other place. Where have you seen this construction? This construction